Here's a short outline of the presentation. I'm going to start with an introduction before we move to an ARMv64, ARMv32 comparison. Then I'll talk about the various ways you can use Neon, present a few benchmark results and work I've done on Skia, and give you a few hopefully useful tips about Neon programming. So before we start, I'd like to emphasize this. This presentation is going to be GCC-centric. It by no means reflect the opinion I have of LLVM or CLang. I just happen to have more experience with GCC. It's also going to be not exhaustive. I'll scratch the surface, basically, but I'll try to do it in an interesting way, hopefully. So a few definitions. We're going to talk about the ARMv8 architecture, which has two different execution states. The first one is ARMv64, which is a 64-bit execution state using the new A64 instruction set. Instructions are 32-bit in size, but can access 64-bit values in 64-bit registers. And the second execution state is ARMv32, the 32-bit execution state, which is a superset of ARMv7A. It's backwards compatible and can run ARM and thumb code. So Neon is basically a SIMD instruction set. So what is SIMD? So the idea behind SIMD is to process multiple data using the same instruction. So CSD, which is what you have on most processors, you have only one instruction which processes one piece of data, whereas in SIMD you can apply the same operation to multiple data. Here we have an example on the graph of 4 additions being performed by only one instruction. So I thought I'd give you a little history of ARM's SIMD technology. So in 2001, ARMv6 was announced, and it had some SIMD extensions. They were operating only on the integer registers and could only process integer values. The idea behind this was to process, for example, 2 16-bit quantities in a single 32-bit integer register. In 2004, ARMv7 was announced, advanced SIMD, including the advanced SIMD, aka NEON technology. So it was using a separate bank of registers shared with the floating point unit, had a few specialized load store instructions which were separate from the standard integer load store instructions, and added a lot of processing instructions. Floating point was supported too, and many more features. I'm not going to do an exhaustive presentation. In 2011, ARMv8 was introduced, and with it came an update of the advanced SIMD technology. So we're moving on now to a simple ARMv32, ARMv64 comparison. There are various differences. For example, in ARMv64, the data processing instructions have only one destination register. So things like, for those who know Neon, zip, unzip have been split into two instructions now. They only have 2 source operands, 1 destination operand. You have some new reduction operations. For example, if you want to do the sum of all lanes you have in a vector, you can do it in 1 instruction. You used to need pairwise add instruction to do that kind of things. Neon now supports 64-bit arithmetic in ARMv64, both integer and floating point. There's a new int instruction that you can use to move data from one lane to between arbitrary lanes in vectors. Saturating arithmetic has been extended. Loads and table lookup instructions have been extended too to have a greater capacity. You can load twice as much in one single instruction in ARMv64. And there's also the possibility to have CRC and crypto extensions. One fundamental difference in Neon between ARMv32 and ARMv64 is the way registers are presented to the programmer. So in ARMv32, you've got 16 128-bit registers, which you can view in an aliased way, meaning that the first quad precision register, Q0, can be accessed also using D0 and D1, which are double precision registers, and D1 is the upper part of Q0. In ARMv64, this has changed, and D1 will be the lower part of Q1. This also applies to S registers. So this has forced the need to introduce some new instructions to access the upper part of registers. Floating point has evolved quite a lot, and in ARMv64 now is IEEE compliant, both single and double precision. So this will help a lot to autovectorize, for example. Multiply, accumulate, and multiply, subtract instructions are fused now, which means that rounding only happens once, and you can choose the rounding mode. It's encoded in the conversion instruction, so you don't need to write a separate register. You don't pay the cost, like in floating point, of having to write to a control register to change the rounding mode. And much more extensions have been added. The assembly syntax has been changed also. There are two examples on these slides, which perform basically the same operation. So mnemonics have dropped the V in front of them, and the size of lanes on which you operate are not anymore specified as part of the mnemonic, but as part of the register expression. So it's basically a register qualifier. The 4H means 4 half words here. And previously, it was specified only once as a U16, inside 16 operation. We're now going to talk about the various ways you can use to use Neon. So there are multiple approaches. You can first use libraries, autovectorization, compiler intrinsics, or hand-coded assembly. What you're going to choose depends on a number of factors. First, the level of complexity of the code you're trying to vectorize, then the time you have, the skills you have, and how close you want to get to the optimal performance. Hand-coded assembly will obviously require more time and more skills, for example. First way is using libraries. So you need a lot less expertise. You just need basically to link against a library and update your code to use the right functions. You get improvements with updates. So basically you get some more speed up for free when a new version of the library comes up, essentially. And I'd like to present, I'm not going to give an exhaustive list of libraries that use Neon, but I'm only going to present one which is maintained by ARM, which is called NE10. It has a very good FFT, fast Fourier transform implementation. It can do general math, image processing, resizing, for example, and is growing currently. So you'll see more features being added to it. The QR code should point you to the GitHub of the library. It's completely open source, so you can access it, modify it.
Does it have?
Does it have?
Does it have 3% transfer? Yeah.
Sorry.
DCT? You said.
Oh, no, I don't think so. So the question was, does it have DCT? And the answer is, I don't think so. You can double check, but. The next way you can use Neons is autovectorization. There's potentially a small engineering cost because you have very little modifications to do to your code, and basically you leave the compiler do the work. If you're using GCC, it mainly boils down to using -03, which triggers F3 vectorize. Unfortunately, everything is not wonderful in this world, and not everything vectorizes. I would argue that the technology is still in its infancy. Compiler engineers might agree or argue otherwise, but to an end user, there are many things which don't vectorize where you would expect them to vectorize. And most of the time, you have to help the compiler. So we're going to explore a small example of autovectorization. Here's a very small and simple function whose purpose is to add two vectors of 16 bits values. So it's written in a very naive way, simple for loop, adding one element at a time, and we're going to see what the compiler can make of it. So you build it using an ARMv64 compiler, -03, and this is the assembly you get. So the compiler did vectorize the code. In the grid block you can see, you have load the first vector, load the second vector, add the two, store the result, and return, which is what you expected. But you have also two different big blocks which you didn't quite expect, the orange one and the purple one. So basically what happened is that to vectorize this loop, the compiler has to transform a sequential operation, which is 4 sequential additions, into a parallel operation where all additions happen at the same time. And it can do it only if it has some guarantees about the code and how the memory is accessed, which it didn't have here. So what happened is that it inserted the first orange block to check that if the pointers were aliasing. And if they did, it would fall back to a scalar processing of the code. The reason it does this is that, for example, you can imagine if the pointers are aliasing memory regions, the first store you do during the first addition could modify the source operands for the next one. So you could introduce a dependency between the iterations of the loop, and it's no more vectorizable in this case. So what can you do about it? Because most of the time when you're writing that kind of code, you know that your memory regions don't overlap, so you need a way to tell it to the compiler. And this is where the restrict keyword comes. It's not specific to autovectorization. It's an extension that has been added in a C99 standard, but it was present in some compilers before. So I put two boxes in the slides. The first one is the C standards definition, well, very short extract of the definition of the restrict keyword. If you want to have a deeper understanding, I recommend that if you're feeling brave also, you go and read the whole paragraph in the C standard. I've also included Wikipedia's definition of the C standard of a restrict, which should be more accessible, I believe, and still reasonably accurate for what we are talking about. Here's the modified snippet of code, adding the restrict keyword to each of our pointers. Basically, here we are making a promise to the compiler. We are telling the compiler these pointers will never be used within the scope of the function to access overlapping memory regions. So it has the guarantee it can transform the sequential set of operations into a parallel one. And this is the assembly we get. We get only the 5 instructions we expected, which are in the green block we've had before. So as you might expect, this is probably faster than the previous code.
How does it check for here? Aren't you assuming that it's like a multiple of 4 in the for loop?
It was a fixed number. It was only loops of 4. Yeah. Oh. If you go back to the code, it was a very simple example. Yes?
You only need to restrict the keyword on the target?
It's a good question.
I would avoid writing that.
I think you need it in the source as well. I'll think about it and maybe give you a more accurate answer later. So here's another trick which will answer partly to your question. Imagine you have a function which takes parameters and a number of iterations. In this function, you have a simple loop based on the number of iterations you do, and you do a processing inside the loop. If you know, for example, you only pass count as a number which is a multiple of 4, there's a way you can hint the compiler about this. For example, you can only mask the 2 rightmost bits. So you're telling the compiler this will only ever be a multiple of 4. And this allows the compiler to do some smart things. For example, it can discard a remainder loop. You get smaller code. As a conclusion on this short introduction to vectorization, I'd say it's a complex subject. And this is by no means a detailed introduction. You can find a bit more material in the Neon's Programmer's Guide. And before we move on, I'd like to give you one last tip about this. Sometimes you try to vectorize a loop and it doesn't vectorize, and you wonder why. There are a number of possible reasons. It can be quite complicated sometimes. But there's an option to GCC which you can pass, and will help you do the diagnosis of what's happening. So it will basically print information about what loop it tried to vectorize, what happened, did it succeed, did it fail, why, and it will help you do more about this. The next way you can use Neon is compiler intrinsics. So as a very, very short definition, let's say compiler intrinsics can be seen as a thin layer on top of assembly, but there's a lot more to them. I've included the short examples. a short example. Basically, you include some special header on neon.h. It gives you a few types, like the uint8 times 8t type. This is basically representing a vector of 8 values of 8 bits. And I've included a sample operation under. This is an addition here, where you're adding 2 vectors containing 8 values of 8 bits and storing the result in a similar vector. There are a number of advantages to using Intrinsics. The first and most obvious one is probably readability. Your code is much more readable if you use Intrinsics compared to inline assembly. You can also reuse code a lot more easily by using inline functions and templates, for example, if you do C++. You benefit from type checking, which is very, very good when you develop. In assembly, it's very, very easy to make mistakes and process using different types, different sizes of lanes, and it will work, it will build, it will assemble, but it will do absolutely not what you expected it to do. But this has forced the need to introduce a special intrinsic called vreinterpret, which you can use to do type conversions. Intrinsics are also easier to debug. It's fairly easy to add a printf, dump your register in the middle of your code, and see what happens. They provide some level of portability between V7 and V8. I'm being fairly conservative here. Most of the time, if you take some V7 assembly code, you just rebuild it and it just works in V8. There are, however, a few special cases. We'll talk about them later. You can see also the compiler combine instructions if you're using operators, not exactly intrinsics, but operators. For example, plus operator, you can use it to add 2 vectors. You can use multiply also. And in some cases, the compiler is able to combine the 2 into multiply accumulate instructions. If you use, for example, a lot of inline functions and templates, it's very nice because it can introduce multiply accumulate instructions in places you would never have thought of doing. I, however, recommend that you don't use the divide operator, because even if ARMv8 has a vector divide floating point instruction, ARMv32 doesn't, so you could easily get code and fall back to integer code without noticing it, well, if you don't benchmark. Another advantage of Intrinsics is that you get register allocation done by the compiler. And probably the single most important advantage is instruction scheduling, which you leave to the compiler, and you get it for free, basically. Doing a small comparison with assembly, I'd say that no, assembly isn't better. It's different. It's only as good as a programmer who writes it. And I'd like to debunk a myth here. There's an element of belief or religion. Many programmers jump straight away on assembly, expecting it to be better, expecting to be able to write better code. And the truth is, in many cases, you will have a very hard time to beat the compiler. I'm going to show you a little example of this. Through a simple code snippet which does 888 to 565 image conversion. So you start with pixels, 3 channels, 8 bits per pixel, and you end up in 2 bytes per pixel, 5 bits plus 6 bits plus 5 bits. So the box on the left, which I titled bad, is an example I found in an early draft of the Neon Programmer's Guide. So it shows a simple 5 instruction sequence which you can use to do that conversion. And I've highlighted pipeline hazard you have on the register Q3. I'm not going to go into details here, but I just want to show that by introducing a new register and slightly reordering the sequence of instructions, you get a very nice speed up on the Cortex-A9, 20%, and the most important result here is probably that you get a 5% increase in speed on the Cortex-A15. So basically what that means is that even on a modern out-of-order core, on a very short 5 instruction sequence, instruction scheduling matters a lot. And I think it's a very important result. Although this snippet is using ARMv32 code, the same point is valid for ARMv8. It's really not different. This is a very generic problem. And what happens if you use Intrinsics? Well, Intrinsics only do the right thing here. Well, when I do the right thing is that they produce the same code sequence. There might be a better one. If you find it, please send me an email. I'll be very interested. I think this example highlights quite well the advantage that you get from Intrinsics. Instruction shielding, which is very, very hard to do by hand. This was only a 5-instruction sequence. You can imagine that it's a lot of fun trying to find the optimal sequence on a 50-instruction function. You can spend days on it. However, Intrinsics come with a number of shortcomings. The first one, ironically, is portability. There are small areas where you can write things in different ways. You can write them in a compatible way or in an ARMv8 only way. This can be a problem. There are examples of pieces of code I've written in ARMv8 Intrinsics, and I had to do slight modifications to make them work on v7 hardware and compilers. Another problem is that you get big performance variations across compilers. I've included the small hints as to which version of compilers you should use. Basically, before 4.7, just don't hope anything to work properly. It will work, but you will face a lot of problems. But it also means you have a performance predictability issue. So if you change your compiler, your code can suddenly start to perform differently, which might not be what you want sometimes. Another problem is that register allocation can go wrong. If you put a lot of pressure, a number of variables in a single function, the compiler usually has a hard time doing a good job. And it starts speeding and using memory when it shouldn't. And the last issue I've encountered was around loads and stores. Not all of them are implemented, and you may have to resort to small bits of assembly to do what you want. Despite all this, I still recommend that you use Intrinsics as a first choice, and we'll come back to this. The last way you can use Neon is hand-coded assembly. So I recommend that you use it only if you really, really, really know what you're doing. You have two ways to use it. You can write S files. You can benefit from macros, preprocessor, and C++ integration at the function level. You can also use inline assembly, which is practical because you can only include small bits, a few instructions here and there in your C++ code. The syntax is a bit painful, but you get used to it. It's very practical if you have to mix with C++ code or Intrinsics. And as a warning, what you do in assembly parts is opaque to the compiler. It won't be able to help you. So if you do something not optimal, you won't get any advantage from the compiler. It will use your code as is. So what should you use? Well, it depends on what you want to do, your experience, the time you have. And as a conclusion, I'd say the vast majority of programmers should use compiler Intrinsics with possibly bits of assembly where needed. And that leads me to my conclusion about the topmost key factor to successful use of Neon. That would be pick the right approach for you and your application. It might seem quite dull, but it's not that much. It's quite a good advice. Conclusion would be don't jump straight to assembly. Really consider Intrinsics. Other key factors are probably to read the documentation, experiment, and the last one, benchmark. Don't assume, benchmark. Moving on, I'm going to present some work I've done on Skia and a few benchmark results. I've used Skia as a way to experiment with Neon Intrinsics and analyze the assembly produced. So first, what is Skia? It's a graphics library used in Chrome, Android, Firefox, for example. And my contribution has been to rewrite and tune the majority of the Neon backend. That's a work which represents approximately 6,000 lines of diff. So I added new optimizations, rewrote some, tuned some others. And one thing I'd like to emphasize is that they had very big gains, up to 80% performance improvement just by rewriting to Intrinsics. So you take an assembly function, rewrite it in Intrinsics, it takes you 2-3 hours once you familiar with the instruction set is becomes suddenly 80% faster. That's quite a nice gain. Thanks to this, also I've been able to remove hundreds of lines of code. The 6,000 lines of diff is quite symmetrical, but I've added a lot of new optimizations. So it means I had to remove a lot of them, a lot of existing code also.
So this 80% improvement of code is you replaced vector assembly with Neon Intrinsics, or?
Yes. So it's basically free. I've removed a lot of assembly also, replacing it with Intrinsics most of the time. The end result is faster, more portable, a lot easier to maintain, and much more readable, so it encourages contribution. It's very hard to hope for people to jump into a 50 lines of assembly sequence and hope that they can improve it. Those who have written assembly know that it can be quite hard to go back to a piece of assembly you've written to fix a bug, for example. This is a lot easier with Intrinsics. So I thought I'd give you an overall view of the contribution. And for this, I've taken a snapshot of the Skia source code as of end of August. And I've done a 32-bit benchmark on an ARM Cortex A57-based platform using Skia's NanoBench tool. So what I've done basically is take the code, remove my contribution, and benchmark before, after. So this has had an impact on 28% of the benchmark, having an impact being defined as a 1% or more improvement. And here's what I got. So for new optimizations, I've been able to make some things up to 6 times faster. And the most interesting result here is that existing optimizations can become 3 times faster. So you take an existing piece of Neon code, you tune it, improve it, use Intrinsics, use better instruction shilling, and you can go up to 3 times faster, which is non-negligible. So I won't go into the details of the graph here. It shows the distribution of the speed up and number of benchmarks. I wanted to highlight that you can get very nice speed ups. Finally, I'd like to give you a few tips, which may seem simple, but are in fact quite powerful. I'm currently writing the blog with a lot of similar tips, so it's only the tip of the iceberg. Before we start, I'll highlight the obvious. Get to know the instruction set. Do spend time reading the documentation, the ARM. You might have good surprises. I've included a few exotic instructions. The first one, VQRT-MOH, is a vector saturating, rounding, doubling, multiply, returning the high part. I'm not expecting you to understand what it does, but what I want to say is that if your application needs exactly this, you can imagine you get a very, very nice speed up by using a very specialized instruction like this, instead of doing it in several 4 or 5 different instructions. I've included a few other examples. The last one, for example, is a rounding, shift right, and narrow, and you have loads of this. So the first tip I'd like to give you is think data, not instructions. When you write Neon code, you really want to transform an input into a result. You don't want to select an addition, a shift, multiplication. You want to get from A to B, and there can be unnatural ways. The most obvious example is probably when you use a shift to do a multiply or divide by a power of 2. You don't want a shift, you want to multiply, but you use a shift because it's a lot of the time faster. Think about it, and once again, do spend some time reading the documentation. The next tip would be to use the lengthening, widening instructions, which are not much used in many code I've seen. So say, for example, that you have to add 2 vectors of 8-bit elements, but you cannot accept overflow and wrapping, or you have some next subsequent processing that needs 16-bit data. The naive way you would do it is by extending the 8-bit operand to 16-bit and performing a 16-bit addition. You see that kind of patterns in a lot of code. I've drawn a small graph to help you visualize how data flows from left to right, starting with 2 vectors of 8-bit lanes and ending up with 1 vector of 16-bit lanes. So to do this, you should use lengthening instructions that basically do everything in one go. You start with two 8-bit values, and you end up with one 16-bit values. When I say values, I mean vector of values here. So what you get is one instruction instead of three, a more readable code, probably more power efficient too. It's something really not to overlook. You can improve a lot of existing code using this. Similarly, you have widening instructions. When you have values in a 16-bit, in a vector of 16-bit values and 8-bit values, you can combine the two whilst doing an operation. So once again, don't change the size of the values before you do the operation. Do consider these special operations that can do both at the same time. Another tip would be to try to hoist and group loads. It can be very simple and efficient. On old cores, for example, it was very easy to get a speed up just by grouping loads. Instead of doing two loads, you do one that loads twice as much data at the same time, and it's faster. However, this is not gospel, especially on newer cores, and I recommend that you experiment. Don't just do it and assume it's going to be faster. To be fair to the Clang LLVM guys, I'd say that I've seen Clang LLVM do it. If you use Intrinsics, it can just group two load Intrinsics into one load instruction. I don't think GCC can do it. At least I've never seen it do it. This is a place where you're likely to require bits of assembly to do it. So this is where using wisely bits of inline assembly can really be useful and recommended. And the last tip I'd like to give you is about preloading, which is not a silver bullet. So preloading is a hint instruction which you can use to hint the processor that you need data later. Please preload my data into memory, I'll need it later. The first obvious thing to say here is to benchmark. It used to be very important on some cores, for example, the ARM Cortex-A9, where it was not uncommon at all to just double the speed. You sprinkle a few preloading instructions, and suddenly you double the speed of your function. However, on recent cores, it's a lot harder to use. It's a lot harder to get a benefit out of it. I'm thinking of Cortex-A15 or Cortex-A57. But do consider it, but do try it, but don't assume. Benchmark, it can hurt also. In Skia, for example, there are multiple algorithms where I had to make a trade-off. So I could gain 100% speed up using on a Cortex-A9 using preloading, but I would take a 5% hit on a Cortex-A15. So in this case, it was quite a reasonable trade-off.
Have you seen any Cortex-A8?
Not much. Not used it much. Finally, before I start to take questions, I'd like to recommend that you read those references, starting with the Neon Programmer's Guide, the ARM Neon Intrinsics reference, the Architecture Reference Manual. It should be your Bible here. Do get to know the instruction set. I repeat it a lot of times, but it's very important. The ARMv8 instruction set overview is a useful document, especially if you're going to migrate code from the AR32 to AR64. It has a very nice table of mapping between instructions. And two other articles I also recommend, which are interesting. So thank you for attending, and if you have questions.
Just so you know, on more advanced CPUs, you do not want to use preloading. On x86 CPUs, if you use preload, you're always going to get wrong. The CPU has enough depth in its pipeline to hold an instruction stream that it's going to be able to tell what preloads happen. And its ability to predict what those are necessary to do way better than everything. So just give up. Take out the preloads. Just a bubble in the instruction stream. That'll waste time.
So as a summary, because I guess people didn't, everyone didn't hear, just don't use preloads on recent cores. You're very unlikely to get it right.
So,
something.
But optimizing for 57 or 15. So are you considering the counterparts binary compatible 7 and 53? So what's if so? Any code you write can end up running on the little core, and there all this automatic preloading and deeper pipeline will go away. So how do you recommend to tackle this, to compare and decide? Because the code will be the same.
Well, it depends. If you're doing some really heavy lifting, it's very likely to end up on the big core. So you can target the big core. On the other hand, if you're doing, like I'm thinking of audio, for example, you can most likely end up on the little core, so you can optimize for, well, general advice is in practice you'll end up optimizing for one. Unless you really want to have two pieces of code and a very smart mechanism to switch from one to the other. But I'm not sure it's worth it, honestly. Does that answer your question? Or capacity-wise,
Every code can end up on the wrong type of core,
yes,
just due to the system constraints at the moment.
Yes.
So is there like, say for example, somebody optimizes for a A15, same code runs on A7. They're like study done to basically say that if it's good for A15, it's good for A7.
No.
Considering an intrinsic that might be used in a graphics, which probably will end up running on 57, but also can be used in different piece of code that is mostly running on 53. So inside the intrinsics, what the implementers think about which core they optimize to, because obviously we don't have two types of intrinsic for this type of core and this type of core.
No.
So is it big core usually?
Sorry?
Is it the big core usually?
Is it?
The target, the big core, the 57, for example?
Well, it depends. It depends on your application.
But the intrinsic is the same. The implementation.
The way you write your code is exactly the same. It will just have different performance characteristics. Sometimes if you unroll more, it will perform better on one or the other.
Actually, to follow up his question, I think what he was asking, or at least I would like to know anyway, is whether these intrinsics and libraries are optimized for a particular ARM processor.
No, but you can benefit from the compiler. If you specify an MCPU option, for example, there's a potential for the compiler to better schedule the instruction for one core or the other.
Okay, and then the question I was going to ask, you had a bunch of benchmark results. It appeared from that graph that every single one improved at least slightly. Is that really true?
Sorry?
Every single one of those benchmarks improved. None of them got worse. Is that really true? You had a graph with a bunch of benchmark results.
Yes.
And if you looked at that graph, it looked like what it said was none of all these different benchmarks got worse. Out of all the different, is that really true? That's pretty good if you do something and every single benchmark improves out of like 50 or however many were in there.
I've included only the benchmarks that show a 1% improvement or more. There are benchmarks unmodified, and there are a few, I think, which have seen a regression.
Okay, all right. So that was a slightly misleading chart then. All right, anyways.
To go back to your benchmark question, sorry. To go back to your benchmark questions, I haven't done extensive analysis. I've just done a quick graph for this presentation. Most of the speedups I can explain. I cannot explain any of the regressions. So I will go back to it probably and try to see if it's a real regression or it's a benchmark problem. Sometimes the tests aren't written in a very nice way.
You said that some instructions are available in the 64-bit and not in the 32-bit.
Yes.
one example is like a floating point division or something, or
Yeah.
so is there like an intrinsic for the 64-bit? And basically that won't compile for 32-bit, or it will just produce like.
I don't know if it does, honestly. I don't think it should, because it would be very misleading in this case. You use one intrinsic, you expect one vector instruction. You don't expect a horrible code that will move your data back and forth to integer register.
So you probably have to put like if defs around it or something, or
Have to put?
if def around it? For
If you,
64-bit?
yes, that would be safer.
Do you have any bit reversal operation? No, well, not bit reversal.
Yes.
I'm talking about, when you have to do like FFTs and stuff, you're
Reverse bits in lanes, within
Yes.
lanes, yes, we have.
not just within lanes, but if I have like 8 memory locations and I want to like access them in bit reversed order, do you have that?
I'm not sure I understand what you mean.
We can probably take it offline.
Yes. Any more questions? Okay, thank you all for attending.